All right, so my name is Rohit Pardasani, and I am a full-time instructor with INE. I have 5 CCIs, CCIE in route switch, security, voice collaboration, and service provider. If you want to reach out to me after the webinar, you can always email me at my email address, which is rpardasani@ine.com, or maybe on Twitter, or even LinkedIn. So without wasting much time, let's quickly get started with spanning tree. Now, spanning tree is something that's basically going to help you with whether it's CCNA or even CCNP, the in-core, or even your CCIE enterprise. So it's again a small topic, but it's still relevant to the new blueprint. Now, the first thing that actually comes to our mind is what exactly is spanning tree? Why do we need spanning tree? I mean, technically, we don't really need it now. It's kind of old technology, but it's still relevant. So why do we actually need spanning tree? The whole reason for spanning tree to exist is to prevent loops when you have redundant links between switches. Now, obviously, if you look at any kind of environment, whether you have a small enterprise or a large scale enterprise, you would definitely have 2 or 5 or hundreds of switches. And obviously you would have redundant links between them. So without spanning tree, what's going to happen? The minute you start creating VLANs and traffic is flowing between switches, if the redundant links are not blocked in using some kind of mechanism, there would definitely be a loop. So spanning tree basically blocks or prevents loops by blocking one or more of the links. So how does spanning tree actually do that? So the first thing spanning tree does is it kind of elects something called as a root bridge. Let me in fact draw it out for you. I'm going to go back here and let's draw it out. So the first thing what spanning tree does is he elects a root bridge. So what exactly is a root bridge? Let's say if I have 3 switches. I have switch 1, switch 2, and maybe switch 3. They all are interconnected. Now, this kind of an environment, there would definitely be a loop, right? Because imagine if I have a PC here who wants to communicate maybe with a PC here. And how does a switch normally behave? When he gets a frame or an ARP request from a PC asking, who is 10.0.0.2? Maybe this is 10.0.0.2. When he sends an ARP request, the switch 2 does not really know that where is that device because he's not really heard about that device ever. So switch 2 is going to send a broadcast, and he would send the broadcast to all the ports in that VLAN, except the port on which you received the packet. So he would send a broadcast, and then switch 1 learns about the broadcast. He would probably send the broadcast ahead. So he forwards it here. This guy would probably forward here. Switch 3 may probably reply back here. He would reply back here. And eventually what's going to happen is that there would be a loop because the CAM table would constantly be updated. Now, what spanning tree does, it basically prevents this loop when you have redundant links by maybe blocking one of the link. The question comes, how does spanning tree block that link? How does he actually choose which link to block? I can't just randomly select any one link, right? There has to be some kind of mechanism. So as you know, all switches exchange BPDUs, which is Bridge Protocol Data Unit. So every switch is actually exchanging that. Your routers and PCs or end hosts do not send BPDUs, only switches send BPDUs. So as soon as the link comes up, every switch by default assumes that I am the root bridge. Now, what exactly is the root bridge? Think of the root bridge like maybe a king. So root bridge is the device that basically decides which port is going to go into blocking state and which port would be in forwarding state. It is the root bridge who basically decides that. So think of the root bridge like the king, and think of a VLAN as maybe a kingdom. So I have root bridge, which is equal to a king. I have VLANs, which is equal to kingdom. So think of it that way. Can I have two kings for one kingdom? No, there can only be one king. I could be a king for multiple kingdoms. So I could be the root bridge for multiple VLANs. But for one VLAN, there can only be one root bridge. So what's going to happen here, how spanning tree blocks or prevents loops, is that the first thing he does, he elects a root bridge. Now, all switches by default, they would say, I am the root bridge, because they all want to be the root bridge. Who doesn't want to be the king? So every switch is going to say that I am the root bridge, but there can be only one root bridge. So election process starts, spanning tree starts the election. We'll still talk about the spanning tree modes a bit later, but just the working of spanning tree is what we're talking about. So spanning tree starts the election process, which basically says, okay, there are three people who are wanting to be the king. There can only be one king or one root bridge. So let's start the election process. So election process starts. Now the selection criteria for root bridge selection is based on two things. The first one is lowest system priority. So system priority, that's the first criteria. If that is the same, it goes to the next criteria, which is lowest MAC address. So two criteria or two selection rules. First, he would always compare the system priority. Now, all Cisco switches, they have the default priority as 32768. And all priorities, it has to be in multiples of 4096. If you look at 32768, even that is a multiple of 4096. 4096 times 8 is 32768. So all switches will exchange in the BPDU. They would basically compare the system priority. Let's say I have not changed or made or manipulated any of my priorities, of my system priority. I haven't changed that. Let's assume that. So if the priority is same, he would compare the MAC address. Obviously, the MAC address is going to be different. So since the MAC is going to be different, one switch gets elected as the root bridge. Let's say switch 1 was maybe having a MAC address of A, maybe switch 2 was B, and switch 3 was C. Maybe this was my MAC address. In that case, because the priority is the same, he would then compare the MAC address. Switch 1 has a lower MAC address. Because of that, switch 1 wins and he becomes the root bridge. So switch 1 would be called as the root bridge. Switch 2 and 3 would be called as the non-root bridges. So non-root bridges. Now, it is the root bridge which basically sends the configuration that how should my port states be? Which port should be in forwarding state? Which port should be blocked? Now, your port state really depends on what kind of mode of spanning tree you're running. So if you look at spanning tree has 3 modes. In fact, Cisco supports 3 modes. We have PVST, which is the default one on Cisco devices, on Cisco switches. We have rapid PVST, which is an enhancement of PVST. And then we have MST, multiple spanning tree. So 3 different modes available. At this point of time, we will purely talk about PVST. We would then move to rapid PVST, and we would then move to MST. So let's say we were running the default spanning tree mode, which all switches by default run. So let's say if you do a write erase to a switch, the switch boots up, and you do a show spanning tree summary, you would see that the default mode is PVST. Now, PVST has different port states and port roles. So once the root bridge gets elected, the root bridge will now decide, okay, how should I should my port be in a forwarding state or should my port be in a blocking state? It's the root bridge who decides that. So what are the states of PVST? Let's see that. So let's write it down here. So I have disabled in PVST, which is basically means it's shut down. So we have disabled, we have blocking, we have listening, we have learning, and then we have forwarding. So disable when maybe your port is administratively shut down. Blocking is where he's not sending BPDUs, but he can receive BPDUs. He's not processing any frames at this point of time. Listening is where he is sending BPDUs, he's receiving BPDUs. He's not learning any MAC addresses or processing frames. Learning is where he is sending BPDUs, he is learning BPDUs, and he is even learning MAC addresses, but he's still not processing the frames. So data traffic cannot be forwarded. Forwarding is where everything is converged, life is good. Where forwarding, you're still receiving BPDUs, you're sending BPDUs, you are still learning MAC addresses if there's something new to be learned, and you're processing or forwarding data frames. So these are the port states of PVST. Now, as far as forwarding is concerned, in forwarding, I have two port rules. I have root port, and I have designated. So two port rules available in forwarding state. Now, if you look at these forwarding states, we have disabled, blocking, listening, learning, forwarding. Disabled, we can set that aside. But if you look at the blocking, listening, learning, forwarding, at any given point of time, your port would either be in block state or it would be in forwarding state. Listening and learning is just a passing phase. You would never see a switch port being stuck at listening or being stuck at learning. Listening and learning is just a passing phase. Again, that how much time it spends on listening and learning, that really depends on your spanning tree timers. Default is 15 seconds for PVST, and learning is also 15 seconds. That's default. So max age is by default 20 seconds in PVST. So the maximum time a port can take to get to forwarding state would probably be about 50 seconds. But that's because of the max age. But if you look at from if you actually count the amount of time it takes for the switch port to go to forwarding state, it would probably be about 32 to 34 seconds, because your hellos are sent every 2 seconds. So 15 seconds for listening, 15 seconds for learning, and then maybe 2 seconds for your hellos, and your port would come up. But theoretically, yes, it's about 50 seconds, max age 20, and listening, learning 15 and 15, which is 30, so total 50 seconds. Now, the root bridge is going to decide what ports go into what state. Now, there are obviously rules for that. There are rules for that. Let me, in fact, wipe this out. So the first rule states that all ports of the root bridge are going to be in forwarding state as designated. That's like a mandatory requirement. All ports of the root bridge are going to be in forwarding state as designated. What is designated? What's the difference between root port versus designated? So root port is the port that goes towards the root bridge. It's basically the best path to reach the root bridge. Designated port is the port that goes away from the root bridge. So since switch 1 himself is the root bridge, he doesn't need a root port, because root port states what? It's the port to go to the root bridge. He himself is the root bridge. So the first rule states that all ports of the root bridge are going to be in forwarding state as designated, which means going away from the root bridge. So this becomes designated. Let's write it down. and designated. Both the ports are in forwarding state. Now, why is that? Because all traffic from a non-root bridge, it transits the root bridge. So let's say if switch 2 wants to communicate with switch 3, it has to transit the root bridge. That's why the port of the root bridge has to be in forwarding state. So that's the first rule. The second rule states that elect one root port per non-root bridge per VLAN. Now, PVST is what? Per VLAN spanning tree, right? The minute I create the instance, spanning tree gets activated. Spanning tree is directly dependent on your VLAN creation. So if I have 5 VLANs, I would have 5 spanning tree instances. And obviously there would be a separate election process for root bridge selection, port selection, all that would be separately done for every VLAN. So let's say we are talking about a specific VLAN, maybe VLAN 10, and switch 1 is the root bridge for VLAN 10, assumingly. So what switch 1 is going to do, after he makes his port into forwarding state as designated, he would now elect a root port on every non-root bridge for that VLAN. Now, there can only be one root port per VLAN, only one root port. I could have multiple root ports if I want to achieve load balancing, but not for the same VLAN. It's going to be for different VLANs. But let's assume we're talking about just VLAN 10. So switch 1 is going to now elect a root port. Now, what's the criteria for root port selection? For root bridge, it was lowest system priority. If that's the same, then lowest MAC address. But for root port selection, the criteria is different. So the first thing that, let's in fact clear this out. So the first thing that my switch 1 is going to do is he will compare the cost. So the first criteria for root port selection is lowest STP cost to root bridge. Remember, it's not interface cost. It's not like bandwidth or interface cost like OSPF or EIGRP. It's STP cost. Spanning tree has its own cost depending on the interface type. For example, if you have an Ethernet, the default cost is 100. If you have a fast Ethernet, the default cost is 19 versus gig port or 10 gig ports. So there is a fixed cost. You can change that, but default is maybe 100 for Ethernet and maybe 19 for fast Ethernet. Let's assume all my links are fast Ethernet. Let's assume that, though you would not find that anymore. But maybe I'm like an old switch. So the first thing he would do is compare cost, STP cost. So cost is based on local interface spanning tree cost plus advertised cost. So it's not just your cost. It's an accumulated cost, your interface spanning tree cost plus advertised cost. So let's look at switch 2. So switch 2, assumingly all these links are fast Ethernet, what's the cost going to be on this link? It's going to be 19. What is switch 1 going to advertise to switch 2? A cost. He himself is the root bridge, right? So he would advertise a cost of 0, which means total cost for switch 2 to reach switch 1 on the direct link is 19 plus 0, which is 19. Now he will look at the cost on this link. What's the local cost on this link? 19. What's the advertised cost by switch 3? Now for switch 3, his local cost is 19. Advertised from here is 0, which means for him, total cost is 19. So he would advertise 19 to switch 2. So switch 2, to go to switch 1 through switch 3, my total cost becomes 38. The cost is different. Since the cost is not the same, lowest cost wins. So this port goes into forwarding state, or in fact, in forwarding state as root port. So this becomes the root port based on cost. Same thing here. This port becomes the root port based on cost again. So now I have this link left, which is between switch 2 and switch 3. Which port becomes designated? Which port becomes blocked? So rule number 2 was elect the root port. The criteria was lowest cost to the root bridge. Now, what if that was the same? If that was the same, it then compares lowest bridge ID. Now, bridge ID consists of 2 parts. So in bridge ID, he would first compare the system priority. So system priority. If that is the same, then he compares MAC address. Lowest wins. So bridge ID consists of the priority plus the MAC address, but he always gives preference to the system priority versus the MAC address. So if, let's say, my cost was the same, he would then go to the bridge ID. And if that is the same, he then goes to the third criteria, which is lowest port priority is what he would look at. The lowest port priority. The port priority is based on, again, 2 things. It actually consists of 2 things. One is the port priority value, and one is the port instance or ID. So default is 128 dot the port number. Again, the port number actually depends on the port instance ID, depends on the type of switch. So let's say if I had a switch which has 24 fast Ethernet ports, no gig ports. So port number 22 would be 128.22. But let's say if I had a switch which had 24 fast Ethernet and maybe 2 gig ports. In that case, the first gig port would be 1, second gig port would be 2, and the fast Ethernet 0x1 would be 3, which means port number 22, fast Ethernet 0x22 would be 24. Again, this is something that you can actually verify by doing a show spanning tree interface detail, and you'll get the port instance ID number. You cannot change this, but you can change this value. You can modify that for port selection. So anyway, coming back to root port selection, it's based on 3 things. Lowest cost to the root bridge, if same, lowest bridge ID. In bridge ID, he compares the system priority first and then the MAC address. If that's the same, then he goes to the lowest port priority, where in the port priority, the 128 or the port priority value, that gives preference over the ID, the interface ID. So once my root port is selected, it now needs to elect on this link which port goes into designated and which port goes into forwarding or as blocking. Now there's a third rule which says that every link must have one and only one designated port. So you cannot have, both these ports cannot go into blocking state. There must be one designated port for every link. Both these ports cannot go into designated because there must be only one. You cannot have 2 designated. You cannot have 0 designated. There must be one and only one designated port per link, which basically means that either switch 2 becomes designated and switch 3 goes into blocking state, or switch 3 becomes designated and switch 2 goes into blocking state. So which one? Again, for designated and blocking state selection, the criteria is still the same. It will compare the lowest cost first, not cost of the link, but the lowest cost to the root bridge. What is switch 2's cost to root bridge? The best part cost. It is 19. What is switch 3's cost to root bridge? It is 19. Cost is same. It now compares bridge ID. What is switch 2's system priority? 32768. What is switch 3's system priority? 32768. It's the same. What is switch 2's MAC address? BBBB. What is switch 3's MAC address? CCCC. switch 2 is lower. So based on bridge ID, switch 2 wins and he becomes designated, and switch 3 goes into blocking state. So this is basically how it works, whether it's PVST or rapid PVST or even MST, the selection criteria is still the same. Obviously the port states would be different, but the way it decides the root bridge or the way it decides which port goes into forwarding state and which port goes into blocking state, that's still the same. So I'll quickly repeat that. Root bridge, lowest system priority, if same, lowest MAC address. That's it. For root port or designated port selection, first is lowest cost to the root bridge, STP cost to the root bridge. If same, lowest bridge ID. If same, lowest port priority. Let's in fact look at some examples to quickly understand what I just discussed. We'll look at some configuration examples before we go to the switch, configure STP, and then verify if what I say is true. So let's look at some examples. Maybe I have, this time I'll take 4 switches. Let's take 4 switches. Okay. So switch 1, maybe I have switch 1 here. I have switch 2, switch 3, switch 4. Let's say I have one link between them, one link here, one link here, and one link here. Let's assume that all switches have the default system priority, which is 32768. That's my default priority. And let's assume that all the links are, let's assume Ethernet, which means my STP cost for every link is going to be 100, correct? And let's assume that the MAC address of switch 1 is A. This is B, and this is C. This is D. Okay? So obviously there's going to be a loop, right? So STP kicks in. When does STP kick in? When does it come in or gets activated? The minute I create the VLAN. Let me in fact quickly show you that. I'm going to go back to, before I show you this example, just quickly go back to my switch. And if I look at my show spanning tree, let's say VLAN 35, it says there's no spanning tree instance for VLAN 35. Why is that? Because the VLAN doesn't exist, right? If you remember, I told you it's PVST, per VLAN spanning tree. The minute I go and create VLAN 35 and exit out, and if I do a show spanning tree VLAN 35, now the instance exists. So that's why it's called as PVST, it's per VLAN spanning tree. The minute I create the VLAN, the instance gets activated. Let's go back to our slide, to our example. So here, based on this diagram, the first thing what spanning tree is going to do for a specific VLAN, it's going to do the same thing for all VLANs, but individually, separately, because it's PVST. So the first thing spanning tree does is elect a root bridge. Now, based on this diagram, who is going to be the root bridge? Let's think about it. So system priority, same of all the switches. Now it compares MAC address. Switch 1 has a lower MAC address, right? So switch 1 wins and switch 1 becomes the root bridge. And switch 3 would be the non-root bridge. Switch 4 would be the non-root bridge. Switch 2 would be the non-root bridge. Now, port states. What's the first rule? All ports of the root bridge, they're basically in forwarding state as designated. So this goes into designated. The second thing that we need is a root port for every non-root bridge. So let's start with switch 2. Switch 2 will first look at, okay, I have two ways to get to the root bridge. I could go directly to switch 1, or I could transit switch 4, switch 3, and then reach switch 1. So now he first compares cost. What's my local cost? Since it's an Ethernet, local cost is 100, advertised cost is 0, so total cost on the direct link STP cost is 100. If I go through switch 4, local cost is 100, advertised cost is 200, because switch 4 has a cost of 100 plus 100. So total cost becomes 300. So obviously this port becomes the root port based on cost. See, it's really important for you to know how to calculate that which switch would become the root bridge. Because if you look at it from a CCNP perspective, you may have questions about this. Maybe they give you a diagram and ask you what port states or which switch is in what state. So it's really important for you to know how to get that. And you should know the correct reason why. So the reason switch 2 selects the direct link is because of cost. Let's look at switch 3. Switch 3 also selects this port as the root port based on cost. Now let's compare switch 4. Switch 4 has two paths. It could transit switch 2 or it could transit switch 3. It first compares cost. What's the cost on the left side towards switch 3? 200. What's the cost if it goes through switch 2? 200. Cost is same. It now compares bridge ID. Bridge ID of who? Neighbor. It compares the neighbor's bridge ID. So switch 2's, what's switch 2's system priority? 32768. What is switch 3's system priority? 32768. System priority is the same. It now compares MAC address. What is switch 2's MAC address? CCCC. What is switch 3's MAC address? BBBB. So based on the bridge ID MAC portion, this port becomes the root port, which is the root port, not based on cost. This was based on bridge ID. And in the bridge ID, the MAC portion, not the system priority, because system priority was the same. So based on MAC address, switch 3 had a lower MAC address than switch 2. That's why that port became the root port. So now I have all the root ports. All I need now is to make designated ports and define which port is going to be blocking. What was the third rule after we select the root port? Every link must have a designated port. So if you see here, on this link, I have designated. On this link, I have designated. On this link, here's a root port. So this has to be a designated port. It has to be, because there must be one designated port. Now I have this link left. This link, again, which port? Both cannot be designated. Both cannot be blocked. One has to be designated. One has to be blocked. So which one? So again here, switch 2 would say, my cost to the root bridge is 100. Switch 4 says, my cost to the root bridge is 200. Remember the cost, it's a common misconception that people always look at the cost of this link. It's not the cost of this link. It's the lowest cost to the root bridge. So whichever is your best path cost, that would be compared. So switch 4 says my best path cost is 200, 100 plus 100. And switch 2 says my best path cost is 100. So switch 2 wins. And based on cost, switch 2 wins and he becomes designated and switch 4 goes into blocking state. Okay, let's see one more example. This time I'll make a bigger topology with multiple redundant links just to get this right. So let's make switch 1. So I have switch 1 here. switch 2, let's say switch 3, switch 4, and let's say switch 5. Let's make one more here, switch 6, and switch 7. Let's take one link here, one link here, one link here, one link here, maybe one link here, one link here, two links here, one link here, one here, and two links here. Okay? Let's also change some system priority. Let's assume that we have changed the default system priority of switch 1 to be 4096, and the MAC address is let's say switch 2 is, let's keep this as 8192, and the MAC address is B. Switch 3 is default 32768. Switch 4 is default 32768. And the MAC address of switch 3 is 0003 dot something. And this is 0004. And this is going to be, again, 32768, 0007. And let's put this as 32768, 0016, or in fact 06. And let's keep this as 32768 as 0015. Okay? And all my links are fast Ethernet. And let's also do one thing, just to make it a bit more interesting. I will write down the port number. So let's say this was fast, or maybe Ethernet 0 by 0 on both sides. This was 0 by 1. This was 0 by 2. This is 0 by 3. This is 0 by 4. This is 0 by 5, 0 by 6, 0 by 5, 0 by 6, 0 by 7, 0 by 8, 0 by 8, 0 by 7. And let's say this was 010, 011. And assuming you all are Ethernet segments, so cost is 100. And let's keep this as 012. Okay, so let's do this. So which switch is going to be the root bridge? That's the first thing we always elect. The root bridge. Based on this diagram, based on system priority, switch 1 wins because he has the lowest priority, 4096. So switch 1 is clearly the winner based on priority, not the MAC address, because he would not compare the MAC address if the priority is not the same. So switch 1 would be the root bridge. All ports become designated. Now let's start electing root ports. Let's start with switch 2. So switch 2 has 3 different paths to reach the root bridge. It could go direct, or it could go through switch 3, or it could transit switch 4. Direct link has a total cost of 100. Through switch 3, total cost is 200. Through switch 4, total cost is 200. So obviously he would select the direct path based on cost. So based on cost, this becomes root port. On switch 3, direct path based on cost becomes root port. On switch 4, direct path based on cost becomes root port. Now we have switch 5. Always elect all your root ports first. First elect root bridge, then make all the ports into designated, and then elect your root ports. So on switch 5, I have 3 links again, 2 direct links and 1 through switch 6. If he goes through these two links, total cost is 100 plus 100, 200. So if he goes from 5, the link 5, the total cost is 200. If he goes from 6, total cost is 200. If he goes from 6, it's 100 plus maybe 100, 200, 300, 400. So obviously this link is eliminated based on cost. These two links would be selected. Now obviously there cannot be two root ports. So these two links, they both have the same cost. So now he would compare bridge ID. So on port number 5, who is the neighbor? Switch 3. What's his priority? 32768. On port number 6, who's the neighbor? Switch 3. What's his priority? 32768. Priority is same. Now compares the MAC portion in the bridge ID. On port number 5, who's the neighbor? Switch 3. What's his MAC address? 0003. On port 6, who's the neighbor? Switch 3. What's his MAC address? 0003. So bridge ID is the same. Now he compares the port priority. So the port priority of this link of 5 would be, let's assume we haven't changed anything. Default is 128.5 versus 128.6, which is lower. This is lower, right? So this port becomes root port. Okay? Obviously, this has to be designated. On this link, it's a pretty clear, obvious reason why switch 3 would be the winner because of costs. What is switch 3's cost to root bridge? 100. What is switch 5's cost to root bridge? From the root port link, 100 plus 100, 200. So obviously he has to go into blocking and he would go into designated. A quick way to remember this is all your upstream switches will always be designated. For switch 5, the upstream switch is switch 3. So all the ports of the upstream switch will always be designated. Now the question comes is, okay, so this was selected based on port priority, correct? Let's move on here and we'll see a bit difference. Let's talk about switch 6 first. So which one is going to be the root port? If he goes from the left side, it's 100 plus 100 plus 100, 300. If he goes from the right side, it's 100 plus 100 plus 100, which is 300. So cost is same. Let's compare bridge ID. Left side, bridge ID priority is the same with the right side. Let's compare MAC address. Left side MAC address is 0015 versus right side MAC address is 0007. So right side wins because cost was same. So this becomes the root port and this goes into designated. We'll talk about this later. Let's select the root port on switch 7 now. Now again, if you remember I told you upstream switches, they are always designated. So this automatically becomes designated. Upstream switches will always be designated. The blocking would be on the downstream switch. So on switch 7, I have two links. Total cost on both the links, 100 plus 100, 100 plus 100, 200. Cost the same. Now compares bridge ID. On both the links, the neighbor is switch 4. So bridge ID, priority, and the MAC address is going to be the same. Now it compares port priority. So when it compares the port priority, you would see that port number 8, whose local port priority value is 128.8, and on 0/7, local port priority value is 128.7. But still, this port would become the root port and this would go into blocking state. There's a reason for that. Port priority is never compared with the local settings. So basically switch 7 would not look at the local port priority. Port priority is advertised by the upstream switch. So switch 4 is advertising a port priority on the left link as 128.7 and on the right link 128.8. So that's why the left link becomes the root port based on port priority. Lowest value wins. So cost is always local cost plus advertised cost. And bridge ID, you always compare the neighbor's bridge ID. And same thing with port priority. It's the upstream switch which advertises a port priority to you. Okay? So this is, we have our root ports now. Now we need to define the block ports. So let's start with switch 3. So let's talk about this link between switch 2 and 3. What's the cost of switch 3 to the root bridge? Direct link cost, 100. What is switch 2's cost? 100, same. What is switch 2's bridge ID? 8192 versus 32768. Switch 2 wins based on bridge ID priority portion. So he becomes designated, this guy goes into blocking. Let's now compare switch 2 and 4. What is switch 2's cost to root bridge? 100. What is switch 4's cost to root bridge? 100. Cost the same. Let's compare bridge ID. Switch 2 has a lower bridge ID than switch 4 because this is 8192 versus 32768. So switch 2 wins, designated, and blocking. Okay. And the next thing that we will look at is between switch 3 and 4. Between 3 and 4, again, the cost is the same. And if you look at the bridge ID, system priority is the same between both the switches. Switch 3 has a lower MAC address, so this becomes designated. This goes into blocking. What else do we have left? I think it is between 5 and 6. 5 has a cost of 200. 6 has a cost of 300. So based on cost, switch 5 wins, and this goes into blocking. Now, PVST is significantly different. All the selection criteria is pretty much the same, whether it's PVST or rapid PVST or even MST. The only difference is from perspective of the topology change notifications. So PVST, you're basically sending topology change notification towards the root bridge. And in rapid PVST, you're actually sending it everywhere. That's why the convergence is much faster in rapid PVST. Okay, so this was getting to know about the basic of spanning tree. Let's quickly lab this up. We will quickly lab this up with PVST first, and we'll quickly look at the enhancements, then move on to rapid PVST, then move on to MST. Okay, let's go back to our switches. Now this is my diagram. I have 4 switches at this point of time. And these links, the cross links, are basically shut. So the only links that I have between switches, which is pre-configured with trunking, is the link between switch 1 and switch 2, 2 links there, 2 links here, 2 links here, and 2 links here. Okay, the cross links are basically shut. Now let's do one thing. Let's make switch 1 into the root bridge. Like I said, you could change the default behavior or influence a switch to be the root bridge. There are 2 ways to do that. I could go and give the command priority. So I could go and change the priority statically, or I could use the root primary command to change my priority automatically based on probes. So 2 ways of doing that. Let's in fact make switch 1 the root bridge. So we will make him the root bridge, and we'll make switch 2 as the backup root bridge. So in case of switch 1 fails, switch 2 becomes the root bridge. So to achieve that, I could go and change the priority by setting this to maybe 4096 and maybe setting this to 8192. I could do this by setting an absolute value with the priority command or by giving the root primary command. Let's look at both of them. So I'm going to go back to my switch, and on switch 1, at this point of time, If I look at switch 1 and do a show spanning tree, let's go back. Run section spanning tree. I believe I don't, I have PVST running. And if I do a show, let's do a show spanning tree summary first, just to quickly show you that PVST is the default mode which is running. And PVST does not have any enhancements by default. So uplink fast, backbone fast, or port fast, they all are going to be disabled by default, unlike rapid PVST, where we have some enhancements which are built in rapid PVST. So if you want to make switch 1 the root bridge, I could go and give the command spanning tree VLAN. I could make switch 1 the root bridge for all the VLANs, or if I do want to achieve maybe some kind of load balancing, I could make switch 1 the root bridge for maybe VLAN 1 to 10, and maybe switch 2 the root bridge for VLAN 11 to 4094, and they be backup for each other. So I could do that. So maybe I say spanning tree VLAN 1-10, and I could say priority and set the priority to an absolute value. Again, like I said earlier, that you cannot give any number. I can't just say 45 or 345. It has to be in multiples of 4096. So priority, I could go and say 4096, and then say spanning tree VLAN 11-4094, priority 8192. And same thing I could do on switch 2, where I could go and say spanning tree VLAN 1-10, priority 8192, and spanning tree VLAN 11-4094, priority 4096. So what effectively happens, I'm kind of doing load balancing now. I'm actually using all my switches. So traffic for VLAN 1 to 10 would transit switch 1, because switch 1 is the root bridge. And traffic for 11 through 4094 would transit switch 2, because switch 2 is the root bridge. So I'm kind of doing a load balancing of my VLANs across my switches using spanning tree. So one way is setting an absolute value for a switch being the root bridge, or I could give the root primary command and the root secondary command. That also would do. The only difference is that if I give the command root primary, then the switch is going to check the priorities of all the switches through the BPDU. And if all the switches are default, which is 32768, in that case, he would reduce his priority by 8192 to a value of, I believe it is 24576. So he skips 1 because you can have a secondary root bridge. So if everybody is default, and if you give the root primary command, he would put his priority automatically to 24576. And when you give the commands spanning tree VLAN X root secondary, this would go here to this value. Okay. So based on this, what I've done is I have made switch 1 the root bridge. So here is the root bridge for VLAN 1 to 10. And so basically this would be designated. And here 19 would be the root port, this would be blocked. Here 23 would be the root port, this would be blocked. And then this one would be root port, this would be blocked. Designated. Here, this would be designated, blocked, and blocked. So this should be my configuration if I actually go and verify my settings. So let's in fact go and check that. If I go back to switch 1 and do a show spanning tree VLAN, let's say 10, all ports, I don't have VLAN 10, let's say VLAN 10. So if I do a show spanning tree VLAN 10, I should see that all my ports are designated, which is as per this diagram. If I look at switch 3, and show spanning tree VLAN 10, I should see that 19 is the root port, 20 is blocked, and the remaining 2 ports are designated, which you can see here. 19 is root port, 20 is blocked, and the remaining 2 are designated. And then if I look at switch 2, VLAN 10, show spanning tree, VLAN 10, you would see that all my ports, except for 24, these 2 ports are designated. This one is root port. So let's go and check that. Show spanning tree VLAN 10. Again, I have 2 designated ports. 24 is blocked. This is root port. And lastly, switch 4, show spanning tree VLAN 10. Let's create that. I would see all ports as blocked except for 1 port, which is the root port. So that matches what we have configured on as per PVST. Now PVST, like I said, it is per VLAN. Okay, so just one thing that you should know is anytime a port goes down, or let's say if I change something, maybe I change the default settings, maybe I change my priority, or I change my cost. Obviously, a topology change notification is sent, and there's a recalculation happening because of maybe some other port would become the root port based on your new cost settings. So root bridge selection is based on your system priority and the MAC address. MAC address you cannot change, but the system priority you can change with the priority command or the root primary command. What about port selection, root port selection? If I look at switch 2, I just want to quickly show you a few show commands that should be helpful. So if I look at switch 2, which is my root port right now, 23, right? What's my cost? It's a fast Ethernet, so 19. Now what you see here, that's your local interface cost. What you see here, that's your total accumulated cost. So never look at this cost, always look at this cost. Okay, in fact, you can see that your root bridge is advertising a cost of 0. Let's verify that with the command show spanning tree interface fast Ethernet 0x23 detail, and let's do include cost, or maybe not. Let's do detail. I should be able to see cost. In fact, it's lower. Cost is in lowercase. So let's try cost. Okay, so I see cost here. Now what you see on top, the first line, if you see here, I see this cost here. This is local cost. This line here, this is what your upstream neighbor is advertising. So who's my upstream neighbor? Switch 1, the root bridge. What is the advertising a cost? 0. So 0 plus 19, total cost 19. Now if I look at switch 4, show spanning tree, let's say VLAN 10. Show spanning tree VLAN 10. If I look here, what's my local cost? 19, root port cost, 19. What's my total cost? 38. How did this 38 come? Because the upstream switch must be advertising a cost. We can verify that with show spanning tree interface 0x19 detail. You would see that the upstream switch is advertising 19. So this line is your upstream switch. This line is your local settings of your local switch. Okay, so your upstream switch is advertising 19. And if you remember, I told you something about that cost can be, that we can actually use cost command in spanning tree to change root port selection. For example, right now on switch 2, my root port is 23. If I want 24 to be the root port, all I would do is change my cost. Let's in fact do a debug first. Debug spanning tree. Maybe we can do BPDUs, and we can probably do, let's say, updates. It's going to be a lot of, so these are all BPDUs. Let's in fact not do BPDUs because you would see a lot of information. And there's not enough time to actually analyze this. Let's do a debug spanning tree and see what we can use. Maybe we'll do events. Okay, and I will go now to my switch, port number 24, or I could go to port number 23 and increase the cost, or I could go to 24 and decrease the cost. So I'll say spanning tree. I could do it for a VLAN by saying VLAN 10 cost. This will only affect that VLAN, or I could do it for all the VLANs by saying spanning tree cost 10, or change my cost. This affects all VLANs versus doing it for just one VLAN, let's say VLAN 10, and cost. I'm going to change my cost to 18. Default was 19. I'm changing it to 18. The minute I do that, if you see there's a topology change notification being sent that, hey, my port cost has changed. And if I do a show spanning tree VLAN 10, you will see that my local cost is now 18. And on this link, it's 19. So obviously, this port becomes the root port. And the 23, which was the root port earlier, goes into blocking state. The only problem with PVST is that there is no uplink fast built in. So if any topology change notification happens, the problem is that the port, which was a root port, goes into blocking immediately, but your port, which was blocking, has not come up yet. It still has to go through STP process of going from blocking to listening to learning and then forwarding, which means you would have kind of a downtime. So obviously uplink fast is something that you should do. You don't have to configure uplink fast for rapid PVST, but for PVST you would need uplink fast if you want the effect of, or if you want downtime to be less. Okay, so port fast was just for edge ports or ports which connect to routers, not for trunk links. Uplink fast is like port fast for trunks, pure trunks. Okay, so I can do cost changes to change my root port, and anytime I make any changes, what's going to happen is that a topology change notification is basically sent, and then the changes take place. Okay, and let's talk about the port priority also quickly before we move on to rapid PVST. So if I look at port priority, let's look at switch 4. Let's do a show spanning tree VLAN 10. And right now, which port is the root port? 19. Let's say I want port number 20 to be the root port. I could go and change the cost locally. That would make switch 4 select port number 20 as the root port based on cost. But I could tell the upstream switch to influence the downstream switch using port priority. So what I could do is go to switch 2 and go to port number 20 and say spanning tree. Again, I could do this per VLAN, or I could do it for all VLANs. This is for all VLANs. Let's do it for a specific VLAN. So VLAN 1 port priority, and define a port priority value. It's in increments of 16. Again, this depends on the switch model. So if it's a physical switch, you may see it as 16 or 32. Virtual switches sometimes show as 64. So always do a question mark and check. This one shows 16. Let's say I'll give increments of 16. Maybe I'll make it as 48. and that's it. I configured switch 2. The effect you would see on switch 4. Show spanning tree VLAN 10, you would see that that port number 20 is becoming the root port. Why is that? Even though locally, my local port priority is higher than this one. If you see, this is 128.22 and this is 128.21. Why is it 22? Because this switch has 2 gig ports. So gig port is given preference. So first gig port becomes 1, second gig port becomes 2, first fast Ethernet becomes 3. So 20 becomes 22. So even though this is higher than this one, he still selects this one. Why? Because port priority is not local. It's advertised by the upstream neighbor. Let's verify that. Show spanning tree, interface, fast Ethernet 0x20 detail. You would see that my local port priority is 128.22, but advertised by the upstream neighbor is 48. So 48.22. So obviously, a lower port priority wins, and that's why switch 4 selects port number 20 as the root port. Okay, so this was PVST. There are no enhancements built in. So port fast is not built in. You have to configure it. Port fast takes the port straight to forwarding state. It does not go through blocking, listening, learning, and forwarding. It goes straight to forwarding state the minute the port comes up. So it jumps to forwarding state. In fact, you can see that when you do a debug spanning tree events, you would be able to see that. And as far as uplink fast is concerned, uplink fast is like port fast for the trunk. In fact, let's in fact look at uplink fast. Just one thing that I am going to do is something about uplink fast. Uplink fast only works for direct failure. It does not work for indirect failure. So for example, let's say if I have 3 switches, switch 1, 2, and 3, and let's say switch 1 is the root bridge designated, root port, and maybe designated and blocked. So if I configure uplink fast, it's a global command, spanning tree uplink fast. It only works for direct failure. So let's say if switch 3's link to the root bridge goes down, what's going to happen behind the scenes? So, I mean, even without uplink fast, eventually this link, which was blocked, would come up as the root port, eventually. But what's going to happen behind the scenes is switch 3, who's lost his connection to the root bridge, will now assume that I am the root bridge, because default behavior of a switch is they always want to be the root bridge. They always want to be the king. So as soon as he loses his connection to the root bridge, he would be like, okay, I've lost connection. The root bridge is dead. I am the root bridge. And he starts sending superior BPDUs. Switch 2 is going to check his connection to the root bridge and then respond back with an inferior BPDU saying, okay, you're not the root bridge. Maybe this link can be opened up. So in fact, this would happen in the opposite way if this link was maybe down and this link was blocked. So with uplink fast, what's going to happen? Let's say if this link goes down, because it's a direct failure for switch 3, it's a direct failure, right? So this port would go straight to forwarding state as root port immediately. There's no delay in going through blocking, listening, learning, forwarding. It's like port fast, jump straight to forwarding state as root port. Now, did any other switch, like for example, switch 1 or switch 2, do they need to change any port states? No, only switch 3 had to change its port state, right? It was a direct failure for switch 3. Uplink fast works. But if this link does not fail, but this link fails, in that case, again, Default behavior would be what? Switch 2 is going to send superior BPDU. Switch 3 will check his connection. Then he will send him inferior BPDU, and then this port becomes the root port. But let's say I have uplink fast. Because of uplink fast, this port transitions to root port, right? But can he transmit data? Because this link is still in block state. Now, two switches need to make changes. Switch 2 needs to change designated to root port, and switch 3 needs to change block to designated. Now, for switch 2, this was a direct failure. So this happens immediately. Okay? But for switch 3, it's an indirect failure. For switch 3, it's not a direct failure, it's indirect. So switch 3 is not going to change this to designated immediately. This would not happen immediately. So uplink fast in this case would not work because for switch 3, it's an indirect failure. It has to go through normal STP process. It has to go. And finally, this would become designated. Okay, that's one thing that about uplink fast. There's one more thing that you should know about uplink fast is that uplink fast adds a cost of 3,000. It adds a cost of 3,000 to downstream switches. Let me in fact show you that. So I'm going to go to all my switches. What's my priority right now? Switch 1 has a priority of 4096. Switch 2 has 8192. Switch 3 and switch 4 are default, 32768, correct? Let's go and configure uplink fast. So spanning tree, uplink fast. Let's go to switch 2, spanning tree, uplink fast. Let's go to switch 3, spanning tree, uplink fast, and switch 4, spanning tree, uplink fast. Okay? Look at switch 1, who's the root bridge? Show spanning tree, VLAN 10. What's my priority? 4096 as per what I had set. What's my cost? 19. Let's look at switch 2. Show spanning tree, VLAN 10. What's my priority? 8192, which I had configured, and my cost is 1819 as per what I had configured. Let's look at switch 3. Show spanning tree, VLAN 10. What's my cost? 3019. Originally, the cost was 19. Local cost was 19. Now the local cost is 3019 because uplink fast adds a cost of 3000 and also changes your priority. It also increases your priority from the default value 32768 to 49152. It increases your priority. The only reason it does that is so that distribution layer does not use access layer as a transit in case of any failures. Okay, and also on switch 4, if I do a show spanning tree VLAN 10, you would see that the cost is 3019 and the priority has changed. Now, if you noticed that the priority and the cost, it only changed on switch 3 and 4. It did not change on switch 1 and 2. Because switch 3 and 4, they are basically access layer switches. Now, how does spanning tree know that? That switch 3 and 4 is basically access layer. So any switch which has the default priority is considered as an access layer switch. Because if you look at it from a production perspective, you would never have a distribution layer switch which may have the default priority. You'll probably have it lower as a root bridge or something like that. Access layer switches, you never change system priority. You keep it as default. So any switch that has a default priority, those switches, for those switches, the cost will increase and the priority would increase. Now, this only happens in PVST. It does not happen in rapid PVST because rapid PVST has uplink fast built in. I don't have to activate it. It's built in. Since it's built in, my cost does not increase. My priority does not change. Everything is happens automatically. So in case if I have a failure of a link, uplink fast would directly change my port to forwarding state. For example, if I go to switch to and do a debug spanning tree events and go and shut down my port 24, which is the root port right now, if I shut this down, you would see that 23 goes straight to forwarding state. So let's do a show spanning tree VLAN 10. So 23 is the root port, and in fact, it's going through listening and learning. Obviously, because this is not it's not an access layer switch. Let me go ahead and do the same thing on an access layer switch, which is switch 4 and switch 3. So 20. Let's bring this back up. I'm going to go back to switch 4 and do a show spanning tree VLAN 10. Here I have port number 20 as the root port. I will shut this and you would see that 19 goes to forwarding state immediately. Let's do a debug spanning tree uplink fast and go to interface 20 and shut this. You should see that due to uplink fast, the port 19 went to root forwarding state immediately. So if I do a show spanning tree VLAN 10, you would not see it going into listening, learning, forwarding. It's straight in forwarding state. And when my port comes back up, it automatically changes back once the port is ready to move to forwarding state. That is uplink fast. I don't have to do that for rapid PVST. Now, if you look at rapid PVST, it's pretty similar. It's still PVST. It's still per VLAN spanning tree. Still the root bridge selection is the same. Still the root port selection is the same. Still your block port or designated port selection is the same. The only difference is that the port states have changed. So we had blocking, listening, learning, forwarding. What they've done is your disabled and blocking and listening, they've combined that into discarding, learning, and forwarding. So only 3 states available. It still has the concept of root port and designated, but we still have an alternate to the root port. So in case if the root port fails, we have an alternate port. And in case if the designated port fails, we have a backup port. So it's much faster in convergence because the topology change notification is sent to all the switches, not just to the root bridge. That's the basic difference. It's still Cisco proprietary. And in fact, if you go to my switch, let me in fact go and show you that quickly, because we're kind of running short on time. Okay, I'm going to go back quickly and change the mode, spanning tree mode, to rapid PVST. Same thing on switch 3, spanning tree mode, rapid PVST. And it is backward compatible. You could still use rapid PVST and PVST. So it is still backward compatible. So spanning tree mode, rapid PVST, and on switch 1, spanning tree mode, rapid PVST. If I do a show spanning tree summary now, you would see that I have enabled uplink fast, but inactive in rapid PVST mode. The reason I get this message is because I had enabled uplink fast. You should not enable uplink fast when you have rapid PVST because that's built in. I don't have to enable uplink fast. So no spanning tree uplink fast. I should not enable it. It's a built-in feature. And lastly, switch 4. So now if I do a show spanning tree summary, you would see that uplink fast disabled, but don't worry about that because it's a built-in feature. It's not going to show up in show spanning tree summary. But if I shut down my link, you would notice that the backup link comes up immediately. It goes straight to forwarding state without you actually configuring uplink fast. That's the advantage of using rapid PVST. It's much faster. If you look at your show spanning tree, let's say VLAN 10, the basic difference is that even though here I actually see that the max age is 20 seconds, the forward delay is 15 seconds, you still see that, but it's not going to use that because the convergence time, if you look at of rapid PVST versus PVST, PVST theoretically took 50 seconds, max age was 20 seconds, versus in rapid PVST, it's much faster. It's about 6 seconds. And my forward delay, there's no 15 seconds as such. So convergence can be as fast as maybe 6 seconds. So less than 10 seconds, you can have convergence, or even 1 second. You can tune that to even 1 second. Okay. Lastly, what we're going to look at is quickly MST. MST is something that is an IEEE standard. So let's say if you were having Cisco and non-Cisco devices, then you would basically use MST. MST is basically instance-based or group-based. It's not per VLAN. By default, there is the default instance, which is instance number 0, MST 0. That's the default. All VLANs belong to one instance only, which is something like the common spanning tree or CST. So by default, it's that. But with MST, you have lots of advantages of MST because it supports faster links. Like PVST had an issue of supporting 100 gig links, but MST can support faster links also. At the same time, it's Cisco, non-Cisco. It supports different vendors. At the same time, if you look at MST, it reduces the amount of CPU that would be required in PVST or rapid PVST. The only reason being in PVST and rapid PVST, I have to process for every VLAN. So every time there's a change, the change happens, there's topology notification being sent for every VLAN separately. So let's say if I have 100 VLANs, which is quite a lot, then I would have 100 instances of spanning tree. And that's something that would cause your CPU to spike up. With MST, I can group all the VLANs into a single instance, or maybe make 2 instances. I don't need 100 instances for 100 VLANs. I could just group them into maybe 3 instances. Maybe I have VLAN 1 to VLAN 50 in instance 1, VLAN 51 to 100 in instance 2, and all remaining VLANs in the default instance 0, which means that only 3 instances of spanning tree would be running. So let me quickly show you that. What I'm going to do is go and change this to spanning tree mode to MST, and also change on switch 3 spanning tree mode to MST. And let's go to switch to spanning tree mode to MST, and switch 1 spanning tree mode to MST. So now I have all my 4 switches running MST, and if I go back to switch 1 and do a show spanning tree and do MST, you would see that I have only 1 instance running, instance 0. and all the VLANs are basically mapped to that instance. Who is the root bridge? Is switch 1 the root bridge? He's not. He's no more the root bridge. If you remember, we did configure switch 1 to be the root bridge, right? If I do a show spanning tree section spanning tree, I did configure switch 1 to be the root bridge. But this command is irrelevant for MST because MST is instance based. It's not VLAN based. It's not per VLAN. So what you need to do is create VLANs, map the VLANs to an instance, and make changes for the instance. So for example, if I want switch 1 to be the root bridge, I would first need to go to spanning tree MST configuration and create instances. Right now, there's only one instance running, which is instance number 0. There's only one instance running. So I would go and create one instance. Let's say instance 1, VLAN 1 to 50. Instance 2, VLAN 51 to 100. And all remaining instances would be in the default one. So if I do a show run section MST, you would see that instance 1 has 1 to 50. Instance 2 has 51 to 100. And the default instance 0 would have all remaining VLANs. So now if I go and do a show spanning tree MST, you would see 3 instances. So I have instance number 0, which has VLAN 101 to 4094, instance 1, which is 1 to 50. I don't see instance 2. The reason I don't see instance 2 is because there is no VLAN for that instance. At least one VLAN must be active. So maybe if I go to switch 1 and say VLAN 51, if I create VLAN 51, then instance number 2 would get activated, which you should be able to see now, instance number 2 for VLAN 51 to 100. The best part about MST is that now, if I go and create a new VLAN, let's say 52, in PVST and rapid PVST, a new instance gets created and BPDUs start flowing, election process starts, my CPU spikes up. With MST, if I go and create now VLAN 52, no changes. MST is already there, which basically maps all the VLANs together into one instance, which is instance number 2. So the only difference is that with MST, the command is different. The concept of root bridge selection is still the same. That's still the same, but only the command is different. I don't give commands like spanning tree VLAN 10 priority. I instead give spanning tree MST instance 1 priority 0 and spanning tree MST instance 2 priority 4096. This is how I would do it. So I do it for an instance, not for a VLAN. Okay. I hope this webinar was informative to you. We could do a lot more things, but again, because of time constraint, I hope you guys enjoyed this. I will now look at some questions that you guys must have put up. Let me quickly have a look at that. All right. So I see a question which says, will STP get recalculated whenever I introduce a new trunk to the environment? Yes, because there could be a topology change notification. Okay, then I have another question is how to avoid spanning tree loops caused by plugging 2 ports to the same phone. So there are many different ways. You could probably have BPDU guard or BPDU filter maybe configured where you could restrict the amount of BPDUs being sent or received on a specific port. So maybe I'm not supposed to be receiving BPDUs from a port which is going to be an access port or maybe a voice port. So I could use BPDU guard for that. Okay, then I have another question. Are BPDUs of different VLANs unique as the system ID for different STP instances will be different? Yes. So, I mean, the BPDU is still the same. It's just that the information about the system ID and the bridge ID consists all of that information. If you actually take a Wireshark capture, you'll be able to see that the BPDU is still the same. It's just that one extra information is available in the BPDU, instructing the remote switch about the VLAN or instance number. Okay, then I have a question. When running HSRP between switch 1 and switch 2 and switch 1 is set on priority, how would the load balance based on priority? So HSRP is going to be mainly at the first hop redundancy, right? So depending on your first hop switch, whichever is the root port, it's going to go towards that. So if switch 1 is your root bridge, that switch which is configured for HSRP towards your end host, it's going to send the traffic towards upstream, towards your root bridge. It's not going to affect traffic towards the end host. It's going to affect traffic towards the upstream switch. I see another question, which is, I see a cost of 200,000 in MST. So that's the default cost in MST. So in PVST and rapid PVST, the default cost for a fast Ethernet was 19. In MST, the default cost for fast Ethernet is 200,000. Okay. I see another question, which is, what is boundary port in MST? So boundary port is something that, let's say if you had a mixed, maybe let's say if you were doing like a migration or something, maybe you had rapid PVST on some switches and you wanted to migrate to MST, or maybe there was a merger between two companies, and one company A was running rapid PVST and company B was running maybe MST. Instead of you having a downtime where you're slowly converting each switch into MST, you could run PVST simulation where the two switches which interconnect, the border switches, one running rapid PVST and one running MST, there on that link you would see boundary ports that it connects towards a PVST domain. Okay, and I see I'm going to take one last question, which is going to be, does it mean that uplink fast enabled, we can't run rapid PVST? No, of course you can still run rapid PVST. It's just that that command of uplink fast is irrelevant. You don't have to do uplink fast. You could still let it be. It's not going to harm you in any way because uplink fast is built in. But the only problem with you giving the command of uplink fast when you're doing rapid PVST, the problem is that because of that command, your access layer switches, their priority would increase, their cost would increase. So it's better to remove the uplink fast and use the built-in feature. All right, so I hope you guys enjoyed, and I would see you in the next upcoming webinar. I believe we have one more today and maybe a few tomorrow and day after. and hopefully you guys can make most use of that. Thank you for attending.